Okay, so taking a look at example 2, we're going to again try to show that the limit doesn't exist, but we'll see that this is a slightly more complicated situation. Okay, so in any case, we're going to basically follow this procedure again, starting with simple paths first, and slowly taking more complicated paths. So let's try to do that. So here again we're approaching the origin, right? So A, B is the origin. So 1, we set y equals 0. So what does it look like? So you have x times 0 cubed over x squared plus 0 to the 6th, and this is the limit as y as x goes to 0 now, right? Because it only contains x. So as always, you don't calculate the limit until you've simplified everything, right? So in the numerator, this is just 0. And then in the bottom, you have x squared plus 0, so that's just x squared. And then 0 divided by anything is just 0. And then finally, the limit of a constant is always just the value of that constant. Okay, so the first path, we get a value of 0. So now we continue. We set x equals 0. So what does that look like? So 0 times y cubed over 0 squared plus y to the 6th. It only contains the variable y now, so this is a single variable limit. I try to simplify as much as I can. 0 times anything is 0 in the numerator, and in the denominator I have 0 plus y to the 6th, which is just y to the 6th, and then 0 divided by anything is just 0, and finally the limit of a constant is just the value of the constant, so that's also equal to 0. Okay, so I mean both of them are the same values, so we haven't gotten anywhere yet. So now we set y equals x. So what does that look like? So that'll be x times x cubed all over x squared plus x to the 6th. It only contains one variable, so this is just a limit for x. Now we simplify. Right, so again, simplify as much as you can before finally calculating the limit at the end. So x times x cubed is x to the 4th, and then on the bottom you can't combine them, so that's just x to the 6th, x squared. Actually, so you can't combine them. However, what we can do is both terms contain x's, so we can factor. So let's factor out an x squared. You're left with 1 plus x to the 4th. So we'll see why we need to factor in a second, right? So by factoring out the x squared, I can now cancel some of the x's. So x squared on the bottom cancels 2 of the x's on top. So what are we left with? All right, so you see how we can simplify it a little bit before doing any calculations. So we get the limit as x goes to 0, x squared on top, 1 plus x to the 4th on the bottom. So now this is as simple as I can get this. So now we calculate. So you just plug in x equals 0. Right, so what do we get? 0 over 1 plus 0. And then this calculates to it's 0 over 1, which is equal to 0. Right, okay, so this this limit is also equal to 0. So they're all the same so far. So you might think to yourself, I mean, all the limits so far is equal to 0, so maybe the limit does exist and it's equal to 0. However, that's not really the case. So why is that? Okay, so I mean, trying all these things is going to be somewhat tedious, and I mean, we don't really have an idea of how to find the right path that's going to have a different value, right? So let's try to compare what's going on here with the previous example to see if we can get some insight, right? So when we calculate the previous example, right? So when we set y equals x, how did this value become a different value than 0? So let's go back to what happened here, right? So when we made the substitution y equals x, the resulting thing that we got here at this step, you can see that we're left with just a single term, powers of x, and it happened that the powers are the same, so that you can just simply cancel the x's, and then the value of the limit is just the coefficients that are left over, right? So just 1 over 2. So that's how we obtained a different value along this path here. So if I want to try to construct a different value, I need to somehow do the same thing, right? So you can see here that when I made the substitution, the powers are sort of mismatched in the numerator and the denominator. So we always ended up getting a value of 0, right? So how can I make the power on the top the same as the power on the bottom? If you notice, if I make the substitution x equals y cubed, so what you'll have is y cubed times y cubed, which is y to the 6th on top, and then here you have y cubed squared, so that'll be y to the 6th also, and then y to the 6th plus y to the 6th is 2y to the 6th. And so with that substitution, I can make it so that it's a single power on top and the bottom with the same degree. So that's what we're going to try. So we're going to set x equals y cubed. So what does it look like? So I already sort of described the calculation, but let's write it out. So it's y cubed times y cubed on top. Then you have y cubed squared here, and then plus y to the 6th. And then this is a limit for y. Okay, so now we simplify, and you'll see that this works out. So y cubed times y cubed is y to the 6th. Here you have a double exponent, so the rule is you multiply, right? So 3 times 2 gives you 6. And y to the 6th plus y to the 6th, those are like terms, right? So that's 2y to the 6th. And so now we have sort of the same situation as we had in the previous example where we obtained a different value, right? So we have a single term power of y that cancels, and so all that's left is the coefficient, which is again 1/2. So this is equal to the limit as y goes to 0 of just the constant 1/2, and the limit of the constant is just a constant. So I get 1/2. Okay, so again, now we have a different value for a limit, so this limit also doesn't exist. So the value of the limit along the last path is different so the limit doesn't exist. Again, this one's a little bit tricky, right? So here I actually had to think a little bit to figure out the correct substitution to make so that I can obtain a different value for the limit.